Hello! In this video, we are going to derive the kinematics equations. Now, in an intro physics course, the kinematics equations refer to equations of motion under a constant acceleration. Now, the average acceleration is equal to change in velocity divided by change in time. Change in velocity is really just final velocity minus initial velocity. I'm going to call the final velocity Vf and the initial velocity V naught. As for change in time, that's just final time minus initial time. Now, the convention we typically use for change in time is we call the final time t and the initial time 0, right? So just like that. Now, we are dealing with a constant acceleration, which means the acceleration doesn't change. Therefore, the average acceleration is equal to the acceleration itself. And I'm just going to call the acceleration a. So really we have that a is equal to Vf minus V naught divided by t. Okay, and so at this point, we're just going to perform some algebraic manipulation. I'm going to start by multiplying t on both sides. And in doing so, on the left side we have at. On the right side, the t's cancel out and we're left with Vf minus V naught. And next, I'm just going to add V naught on both sides. V naughts go away, and we are left with Vf is equal to V naught plus At. And so as you can see, we have derived our first kinematics equation. Now notice, we derived this kinematics equation from the definition of average acceleration. For the second kinematics equation that we're going to derive, we are going to derive it from the definition of average velocity. So, average velocity, if you recall, is change in position divided by change in time. Now, change in position is really just final position minus initial position. And I'm just going to call the final position xf and the initial position x naught. And again, change in time is just final time minus initial time. Using the same convention, final time is just t, initial time is still 0. Okay, but remember, we are working with a constant acceleration. How do we get constant acceleration involved with this? Well, it turns out that under a constant acceleration, your average velocity is really just the average of your initial and final velocities. In other words, it's just V naught plus Vf divided by 2. I could make a separate video deriving that this is what average velocity is under a constant acceleration, but in this video, we're just going to use it to help us derive this second kinematics equation. Okay, so really what we have here is that V naught plus Vf divided by 2 is equal to xf minus x naught divided by t. Okay, now we're just going to perform some algebraic manipulation. So cross multiplying, we have this times this equals this times this. Next, I'm just going to divide 2 on both sides. On the right side, the 2's cancel out, and so we're just left with xf minus x naught. On the left side, we see that we're dividing by 2. I'm actually just going to rewrite that as multiplying by 1/2. Just like that. Next, I'm just going to add x naught to the other side. And just like that, we have derived our second kinematics equation. Okay, so we have 3 other equations to derive. But it turns out, to derive the other 3 kinematics equations, all we have to do is combine these 2 equations together in 3 different ways. Okay, so let's start out by copy and pasting the second equation. Okay, and notice I wrote Vf in a different color. Well, what I'm going to do is I'm going to replace Vf with V naught plus At, because Vf is equal to V naught plus At. Right, just like that. And at this point, we're just going to simplify it. Now notice we have V naught plus V naught. That gives us 2 V naught. And I'm actually just going to move the t out to the front of the parentheses right here. Right, just so it looks nicer. And next I'm just going to distribute it across the parentheses. Okay, so distributing it across, we have 1/2 t times 2v naught. That gives us v naught t. And next we do 1/2 t times at. That gives us 1/2 at squared. And so just like that, we get our third kinematics equation. Okay, let's derive the fourth kinematics equation. Again, I'm going to copy and paste the second kinematics equation right here. But notice, in this case, I've written v naught in a different color. That's because I'm going to take the first equation and I'm going to algebraically solve for v naught. So let me do that real quick. So algebraically solving for v naught, all we have to do is subtract at to the other side. And if we do that, we're left with v naught is equal to vf minus at. So really, all I'm going to do here is I'm going to replace v naught with vf minus at. Okay, and so now we're just going to simplify it. Notice we have vf plus vf. That gives us 2vf. And again, I'm just going to move the t out to the front of the parentheses. And now I'm just going to distribute this across. So first we do 1/2 t times 2vf. That gives us vft. And then we have 1/2 t times negative at. That gives us minus 1/2 at squared. And so this is our fourth kinematics equation. So we have one more kinematics equation to derive. And again, we're going to be combining the first two equations together in some sort of way. Again, I'm going to copy and paste the second kinematics equation right here. Now notice, in this case, I've written t in a different color. That's because I'm going to take the first equation and I'm going to algebraically solve for t. So let me do that first. So to algebraically solve for t, let's start by subtracting v naught to the other side. We're left with vf minus v naught equals at. Now all we have to do is divide a to the other side. And so just like that, we have algebraically solved for t. And so now all we're going to do is replace t with what it's equal to, right? vf minus v naught over a. Okay, so now that we've done that, we're just going to simplify this up a little bit. Now notice we have two fractions, 1/2 and vf minus v naught over a. If we focus on multiplying the denominators, we really just have 2a. So really, I'm just going to rewrite this as 1 over 2a. And from here, what we have left is just v naught plus vf times vf minus v naught. Next, I'm actually just going to flip these two things around. And notice, this is really just vf plus v naught times vf minus v naught. In other words, it's really just in the form of a plus b times a minus b. If you recall, whenever we have something like a plus b times a minus b, this really just gives us a squared minus b squared. So really, this is just vf squared minus v naught squared. Okay, and next I'm just going to subtract x naught to the other side. So we're left with xf minus x naught is equal to 1 over 2a times vf squared minus v naught squared. And next, we're going to eliminate the fraction by multiplying 2a on both sides. And when we do this, notice the 2a's go away. So on the right side, we're just left with vf squared minus v naught squared. And on the left side, I'm actually just going to keep this the way it is. And all I'm going to do is I'm going to add v naught squared to the other side. And so what we have now is vf squared is equal to v naught squared plus 2a times xf minus x naught. So this is actually our fifth kinematics equation. And so yeah, this is pretty much it for all the kinematics equations. And that's how you could derive them, right? We derived this one from average acceleration, we derived this one from average velocity, and it turns out to derive the other three, all you have to do is combine the first two equations together in 3 different ways, right? That's pretty much the idea of how you could derive them.